Imagine accelerating away from Earth at impossible speeds, watching the familiar blue marble shrink beneath you as you venture outward through the cosmos. In the next 10 minutes of reading, you'll travel farther than light itself has traveled in 13.8 billion years. You'll pass planets, stars, galaxies, and structures so vast they defy human comprehension. This is a journey to the edge of everything we can possibly see, the cosmic horizon beyond which even light has not had time to reach us since the Big Bang. Every landmark on this journey is real, mapped by telescopes and measured by scientists. The numbers are accurate, the distances are verified, and the scale is absolutely staggering. First minute. Leaving home, 0 to 20 light hours. We launch from Earth at multiples of light speed, purely imaginative but necessary for our journey. Within seconds, the moon flashes past at 384 to 400 kilometers away. In less than 8 minutes of travel at light speed, we'd pass the sun, our home star, sitting 150 million kilometers, 1 astronomical unit or AU, from Earth. Its light takes 8 minutes 20 seconds to reach Earth. We've crossed that gulf in subjective moments. Mars recedes behind us, then the asteroid belt, a sparse collection of tumbling rocks, nothing like the dense fields of science fiction. Jupiter, the gas giant, orbits at about 5.2 AU. Saturn, with its magnificent rings, lies at 9.5 AU. We blow past the ice giants Uranus, 19 AU, and Neptune, 30 AU, the outermost major planet. But we're barely leaving the neighborhood. The Kuiper Belt, home to Pluto and thousands of icy bodies, extends to roughly 50 AU. Beyond that lies the scattered disk and, much farther out, the theoretical Oort cloud, a spherical shell of icy objects extending perhaps 100,000 AU, nearly 2 light-years, from the Sun. This is the true boundary of the solar system's gravitational dominion. By the end of our first minute, we're just clearing this cosmic doorstep. Second minute, into the stellar void, 2 to 10 light-years. The space between stars is profoundly empty. The nearest star system to our Sun is Alpha Centauri, a triple star system 4.24 light-years away. Its closest member, Proxima Centauri, is a dim red dwarf with at least 2 confirmed planets. At conventional rocket speeds, reaching Proxima would take tens of thousands of years. Even traveling at light speed, it's a 4-year journey. We cross it in seconds. Out here, the Sun is no longer a disk, just a bright star among stars. Barnard's star passes at 6 light-years, a fast-moving red dwarf. Sirius, the brightest star in Earth's night sky, lies 8.6 light-years away, a brilliant white star with a white dwarf companion. The fundamental truth of interstellar space becomes clear. Stars are islands, separated by oceans of near-perfect vacuum. The density of interstellar space averages about 1 atom per cubic centimeter, far emptier than the best laboratory vacuum achievable on Earth. Third minute, the Orion Spur, 10 to 1,000 light-years. We're now deep in our stellar neighborhood, the Orion Spur, a minor spiral arm of the Milky Way galaxy. Stars proliferate, each a sun with its own potential family of worlds. At 37 light-years, we pass TRAPPIST-1, a red dwarf hosting 7 Earth-sized planets, 3 in the habitable zone, one of the most exciting planetary systems ever discovered. At 300 light-years, the Orion Nebula glows, a stellar nursery where new stars ignite from collapsing clouds of gas and dust. It's visible to the naked eye from Earth as a fuzzy patch in Orion's sword. We pass Betelgeuse at 550 light-years, a red supergiant star so enormous that if placed at the center of our solar system, its surface would extend past the orbit of Mars. It's nearing the end of its life and could explode as a supernova at any time, tomorrow or in 100,000 years. By the end of this minute, we've traveled 1,000 light-years. The Sun is no longer identifiable among the hundreds of billions of stars in the galaxy. Fourth minute, crossing the Milky Way, 1,000 to 50,000 light-years. Our galaxy, the Milky Way, is a barred spiral galaxy containing 200 to 400 billion stars. It measures roughly 100,000 to 200,000 light-years in diameter, estimates vary, with a central bulge and sweeping spiral arms. We race across the disk, passing countless star clusters. Globular clusters, ancient spherical collections of hundreds of thousands of stars, orbit the galactic halo. These are among the oldest structures in the galaxy, some nearly as old as the universe itself. At the galactic center, approximately 26,000 light-years from Earth, lies Sagittarius A, a supermassive black hole with a mass of about 4 million suns. We cannot see it directly. Black holes emit no light, but we can observe stars orbiting the invisible gravitational monster at tremendous speeds, some completing orbits in just 16 years. The galactic center blazes with stars packed far more densely than our sparse neighborhood. If Earth orbited a star in this central region, the night sky would contain thousands of stars brighter than Venus, bright enough to cast shadows. Fifth minute, the local group, 50,000 to 5 million light-years. We exit the Milky Way's disk, and the full glory of our galaxy becomes visible, a luminous spiral pinwheel against the black. But we're not alone. At 163,000 light-years, the Large Magellanic Cloud appears, a satellite galaxy of the Milky Way, containing perhaps 30 billion stars. The Small Magellanic Cloud follows at 200,000 light-years. These are visible from Earth's southern hemisphere as hazy patches. At 2.5 million light-years, we encounter Andromeda, M31, the nearest major galaxy to the Milky Way and the most distant object visible to the naked eye from Earth. Andromeda is a spiral galaxy slightly larger than the Milky Way, containing perhaps 1 trillion stars. In about 4.5 billion years, Andromeda and the Milky Way will collide and merge, a slow-motion galactic dance lasting hundreds of millions of years. Andromeda has its own satellite galaxies, M32 and M110, visible as small elliptical smudges. Together, the Milky Way, Andromeda, the Triangulum Galaxy, and about 80 smaller galaxies form the local group, a gravitationally bound collection spanning about 10 million light-years. Sixth minute, superclusters and the cosmic web, 5 to 500 million light-years. Beyond the local group, the universe reveals its largest structures. Galaxies are not randomly scattered. They form groups, clusters, superclusters, and vast filaments separated by enormous voids. The local group is part of the Virgo supercluster, with the massive Virgo cluster at its heart, about 65 million light-years away. The Virgo cluster contains over 2,300 galaxies, including the giant elliptical galaxy M87, which harbors a supermassive black hole. The first black hole ever directly imaged by the Event Horizon Telescope in 2019. Even the Virgo supercluster is just a small part of something larger. Laniakea, a galactic supercluster spanning 520 million light-years and containing approximately 100,000 galaxies with a total mass of 100 million billion suns. All the galaxies in Laniakea are slowly moving toward a gravitational focal point called the Great Attractor. The cosmic web becomes visible, vast filaments of galaxies stretching across hundreds of millions of light-years, surrounding enormous voids containing almost nothing, regions of space hundreds of millions of light-years across, with few or no galaxies. 7th to 10th minutes, the deep universe and cosmic horizon, 500 million to 46.5 billion light-years. We now accelerate through deep cosmological time. The galaxies we see are no longer neighbors. We are observing them as they were billions of years ago, their light having traveled for eons to reach this point. At 2.5 billion light-years, we're seeing galaxies as they appeared when Earth was still a young, hostile world. At 7 billion light-years, galaxies appear as they were before our sun even existed. At 13 billion light-years, we observe the distant universe in its adolescence, galaxies smaller, more irregular, blazing with intense star formation. These are among the most distant galaxies ever observed. And then we approach the edge, not an edge in space, but an edge in time. The cosmic microwave background, CMB, appears as a wall of faint radiation in all directions. This is the afterglow of the Big Bang itself, light that has been traveling for 13.8 billion years, stretched into microwaves by the expansion of space. It marks the moment, about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely. But here's the mind-bending part. While that light has traveled for 13.8 billion years, the space it traveled through has been expanding. The actual current distance to the source of the CMB, the edge of the observable universe, is approximately 46.5 billion light-years in all directions. This is the horizon, not because there's nothing beyond it, but because light from farther away has not had time to reach us. The universe may be infinite, but our view is fundamentally limited by the age of the universe and the speed of light. We've reached the edge, the boundary of everything humans can ever observe. Beyond lies the unobservable universe, forever hidden behind the cosmic horizon, expanding away faster than light can ever close the gap. We are, and will always be, observers of only a finite sphere, impossibly vast, yet cosmically limited. Welcome to the edge of everything,